Okay, so yes, we have our weights, we have our frequencies, and um, we want to draw a histogram. Okay. Now, I have one rule when it comes to histograms. And it's this. The frequency is the area of the bars. What the hell does that mean? What on earth does that mean? Well, if we know the frequencies, which is the area of each of the rectangles that we're going to draw eventually for our histogram, and we know the length, because the weights, the class intervals, would be considered the lengths of our rectangles, or we can just work out what the heights of the rectangles are going to be. So let's go through what I mean. So again, just as a reminder, so we have the frequency, the area of this first one is 20. The weight, or the weight interval is from 0 to 20, right? So we know that the length or the width of the rectangle is 20. It goes from 0 to 20. And we know the area, I'm just going to write this as area, and I'm going to write this as width. We know that obviously the height times the width is going to give us the area. So in this case, it's going to have to be 1, right? The area is 20 divided by the width, which is 20, makes the height 1. So drawing my first bar, that's going to be like that and like that. So that's the first section there. Let's just color that in. I'm going to draw it in different colors just to make it clear and color code. The second one, we've got the width as 5 and the area as 23. So we do the area divided by the width to give us the height. So 23 divided by 5 is equal to 4.6. So we know that for the next one, which goes from 20 to 25, we know that the height is going to be 4.6. So 4.5, 4.6. So 4.6 is about there. And I'm just going to draw a nice straight line. Goes up to 4.6. And remember, with a histogram, the bars don't have to be, they can be like uneven bars, but there can't be any gaps between the bars. Okay, and then the next one, I'm doing it as I go. We go from 25 to 35. So our width there is 10. So our area, 27, divided by our width is going to give us our height. So 27 divided by 10. I nearly used the calculator for that. Wow, that would have been, I don't know. In fact, shameless, please go for it. 2.7. So we go from 25 to 35. And we go up 2.7 high. So that's 2.5, 2.6, 2.7 up here. Like that. And like that. Okay, and then lastly, we've got from 35 to 50, that width is going to be 15. And the frequency is 33, so 33 divided by 15, giving us 2.2. Okay. So our height is going to be 2.2, and it goes from 35 all the way up to 50. And that is our histogram. I kind of forgot to color in. Not gonna lie. Let's just color it in for completeness, because, yep. Now, I'm doing it in color just to show people the different bits. But yes, if you remember the frequency is the area of the bars, that concept can take you a long, long, long way. Now, of course, it does require a lot of practice, but there we go. Okay, next, a sequence of patterns is made using horizontal sticks and vertical sticks. The table shows the number of horizontal sticks and vertical sticks in each pattern. What fraction of the total number of sticks in pattern N are vertical? Give your answer in terms of N. Oof, okay. What's going on here? Right, so the vertical sticks are just going... Okay, so for the vertical, in pattern number 1, it's 2. Pattern number 2 is 3. Then 4. Then 5, and so on. So we need to work out the nth term of this, basically. Yeah, we basically just need to work out the nth term because it's asking for pattern n, isn't it? So the nth term, well, it's going up in ones. So it's 1n. And then what we need to do is write out like the 1 times table. So because that, 1n relates to the 1 times table. So 1, 2, 3, 4, and so on. And we see that our sequence is everything in the 1 times table plus 1. So it's just n plus 1. That's for the number of vertical sticks. Now we also need to look at horizontal because it's asking us for the fraction of the total number of sticks. So we need to look at vertical and horizontal, right? So horizontal goes 2, 4, 6, 8, and so on. Well, that one's quite simple because it's just the 2 times table, so it's just 2n. Right, it's going up in 2s, it's 2n, and that is the 2 times table. So first of all, in the nth patterns for each of them, the total is going to be n plus 1 plus 2n. So that's taking the verticals and the horizontals. And that in total is 3n plus 1. Right? If they're asking for the fraction, 3n plus 1 is the total, so that's the denominator. And for the vertical, well, it's n plus 1. So that is going to be the fraction, and that's in terms of n. And that's good enough for us. So that's it. So that's our final answer. n plus 1 over 3n plus 1. So it's about working out nth terms, basically. All right, let's go on to the next one. Here we have the equation of a curve is y equals 3 to the power of 2x. Y equals 3 to the power of 2x. Okay, so it says circle the point that lies on the curve. But with this one, it's basically saying when x equals this, y is equal to this. We just need to test each one until we get one that actually works. So if x equals 2, does y equal 27? Well, let's try it. 3 to the power of 2 times, not x, but instead we're going to replace that with 2, which equals 3 to the power of 4, which equals 81. That's not 27, so this one doesn't work. Next, 3 to the power of 2 lots of 27. Well, that's going to be a ridiculously huge number, so it's definitely not going to equal 2. So we can disregard that one. Next one, 3 to the power of 2 lots of 2 is equal to 3 to the power of 4, and that is equal to 81, so this one is the one that works indeed. So it seems like they basically just swap the coordinates around, but when x equals the first coordinate, y equals the next one, right? That's how it works. X coordinate, y coordinate. So it works for that one. 23b, a different point on the curve has y coordinates a third. Work out the x coordinate. So they've given us the y coordinate as a third, so we know a third is equal to 3 to the power of 2x. This is interesting because this is like an index law type thing. And one way you can do this is, well, recognize that a third is the same thing as 3 to the power of minus 1, isn't it? And that's equal to 3 to the power of 2x. Now you've got two things, 3 to the power of something equals 3 to the power of something else. So the two powers must be the same. So we can say that minus 1 is equal to 2x. Therefore, minus a half is equal to x. So the x coordinate is minus a half. Okay, let's keep going. Oh, yeah. Next, we've got a to the power of b. Nearly missed the question, actually. A to the power of b equals 5, where a is an integer and b is a proper fraction. Proper meaning that the numerator is smaller than the denominator. Okay, so a to the power of b equals 5, where a is an integer and b is a proper fraction. Work out one possible pair of values of a and b. Okay. What have we got here? This looks interesting. So a fraction. So we could look at like if the answer is 5, which is a whole number, and b is a fraction, so we're looking at fractional indices. This is quite a good question. So suppose we had 25 for a. Well, we know the square root of 25 is 5, but how can we write that? So we know that the square root of 25 is equal to 5. So as indices, the square root is to the power of a half. So 25 to the power of a half is equal to 5. So that means that a could be 25 and b is equal to a half, which is indeed a proper fraction. So that is good enough for us. Now, in case people were thinking, oh, what kind of answers could you have had? Well, you could have had, say, the cube root of something equals 5. Let's say the cube root of 125 is equal to 5, which means 125 to the power of a third, because that's what cube rooting is, would equal 5, in which case you could have that a equals 125 and that b is equal to a third. That also works. Okay, and we can also do similar things, such as the fourth root of 625, and so on and so forth. But I'll leave it there. We've got one possible value. That's kind of what we needed. Next is asking us to expand and simplify this. Well, it's just the triple brackets. So we expand the first two brackets. 2x plus 2 multiplied by x minus 3. So if we expand that, we get 2x times x. So that's going to be 2x squared. Just going to keep changing colors. 2x times minus 3 is minus 6x. Then we have 2 times x, which is plus 2x. And then we have 2 times minus 3, which is minus 6. Right, there are different things. And then we expand and simplify now. We need to collect like terms and everything. So the 2x squared is a nice standalone term. Minus 6x plus 2x is minus 4x. Careful with those minuses. Then minus 6. And now what we're going to do is we're going to take this answer. So 2x squared minus 4x minus 6, and we're going to multiply that by x minus 4. Okay, and then I'm going to go for the process again. This time it's just going to be a bit more. So 2x squared times x is equal to 2x cubed. Changing color again. 2x squared times by minus 4 is minus 8x squared. Changing color again. We have minus 4x times by x, which is minus 4x squared. Changing color again. Let's go for red this time. Minus 4x. Oh, no, not the rubber. Let's go, yeah. Let's go minus 4x times minus 4 is minus plus 16x. Whew, that would have been fatal. Wow. Then let's go for this dark blue. Minus 6. where do I even put it? Well, minus 6 multiplied by x is going to be minus 6x. And then finally, this, not even this, that I don't even know what color that is. Let's go for another color. Let's go for this weird looking one. Minus 6 multiplied by minus 4 is plus 24. So look at all those colors. Hopefully you appreciate it all. And simplify. So 2x cubed is a standalone term. The x squared terms, you've got minus 8x squared and minus 4x squared. So that's minus 12x squared. Then you've got 16x minus 6x, which is plus 10x. Then you've got plus 24. And that's it. We've expanded and simplified fully. So that's our final answer. That's our final answer. So we've got 2x cubed minus 12x squared plus 10x plus 24. Just about able to fit it there. Goodness me. Right, next. Oh dear, this one's like a toughy one. People find this one tough. Here are two similar cones, but it's actually not too bad, to be fair. The surface area of cone A is 5 meters squared, and the surface area of cone B is 7.2 meters squared. Work out the ratio of the radius of cone A to the radius of cone B. So this looks to me, because we haven't got enough information to work out what the radius actually is, or do we? No, we don't. This looks like a surface area, like a scale factor kind of problem, but an area scale factor problem, right? So if we know this one has a surface area of 7.2 meters squared, and this one is 5 meters squared, the area scale factor, so ASF, area scale factor, is going to be 7.2 divided by 5. So that's going to be 1.44. So the area scale factor is 1.44. So the linear scale factor, which is what we're interested in, the linear scale factor, well, that's going to be, what is that going to be? That is going to be the square root of the area scale factor. That's usually how it works. Which in this case is going to be the square root of 1.44, which is going to be 1.2. So it basically means to get from this length over to this length via linear scale factor, we times by 1.2. So the scale factor for the length in cone A, which for radius is a length, is going to be 1. And for the other one, it's going to be 1.2. And that's how that one works. Okay, we've not got too much longer to go. How much more do we have, actually? We've got 27, 28, and 29, and 30, and then we are done. Okay, fine. Just looking ahead here. Okay, so next we've got a vector question. So we've got a diagram, we've got the vector A, B, 5B given to us, and all these kinds of things. And we want to show that dx is equal to 2/5 A plus 3/5 B. Okay, no worries. So what do we know? We know that the ratio of EX to XH is 3:2. So basically, 5 parts, 3/5 and 2/5. 3/5 versus 2/5. It's always good to write these things out because we know it's going to be 3/5 along the way and things of that nature. EF, FG, well, 1, 4, that gives 5, so it's 1/5 to 4/5. So it's always good to recognize these kinds of things. So we want dx. Well, first of all, if we could determine what h to e were, that would be quite useful. So we need that. So h to e, he. So that's going to be, so we can't go directly from h to e. because we don't know that. So we have to go along this way, h to d, and then from d to e. So let's just do that. So that's going to be, h to d is going to be minus b, because you're going in the opposite direction of the arrow of b, plus a, or rather a minus b. So we know that's what h to e is. All right, so we know this bit is a minus b. Okay. Now we can work out h to x, right? H to x. Well, if we know xh, going from here again, we know that let's write it in a different color. H to x, because it's 2/5, it's 2/5 along the way of e to x. So that's equal to 2/5 based on the ratio of h to e of he. So that's going to be 2/5 of a minus b. Okay. Then to work out d to x, well, d to x is just going to be b plus that, right? It's going to be b plus our 2/5 of a minus b. And then we just need to expand and simplify. So that's b plus 2/5 of a minus 2/5 of b. And we have the 2/5 of a. 1b take away 2/5 of b, or 1 take away 2/5 is 3/5. So that's plus 3/5 of b. And that was what we wanted. Okay, and next, is dxf a straight line? Show working to support your answer. So dfx. Is it possible for me to like take a screenshot or something? Or maybe not. Maybe I'm asking for too much. Who knows? Let's see. Maybe. No, not document scanning. That's not what I wanted. Am I asking for too much? Maybe. Okay, we'll leave that one. Fine. Okay, no worries. dfx, right? So we want to show that dfx is a straight line. No, dxf rather. dxf. Well, we've just shown what dx is. Now what we need to do is work out what is xf. So they're asking, is dfx a straight line? So we need to work out what xf is. So xf, let's change the color. So we're going from x to f. Well, first of all, that's going to be x to e. Well, that's one way you can do it anyway. Plus e to f. Right? But before we even work that out, let's just do a bit of working here on the side. So we're going to need this whole length here, e to g. And to get there, we can go from e to d. We can go from e to d. And then go from d to g. dg. Okay, so there we now know the, okay, cool. E to d, well, you're going against the arrow, so that's minus a. And let's make that a bit darker. D to g, well, we're going the b root plus the extra 5b. So in total, it's 6b, right? So plus 6b. So that's going to be, if I just write it like this, 6b minus a, going in that direction. So now that we've worked that out, well, we know that it's going to be xe, going back to our original bit that we wrote, plus ef. Well, based on the ratios, that's a fifth along the way, right? That's a fifth of eg. A fifth of eg. Okay, so xe, that's going to be 3/5 of EH, isn't it? 3/5 of EH. So 3/5 of, HE rather, because it was going along that line that we worked out before. And that's just plus the same 1/5 of EG. Okay. Now, H to E, we did work out, which was A minus B. So it's 3/5 of A minus B, and plus 1/5. EG we worked out to be 6B minus A, so 6B minus A. We worked that out over here. Okay. Then we're just gonna simplify this, right? Because it's, yeah, that's gonna give us what XF is. So that gives us 3/5 A minus 3/5 B. A fifth times 6B is 6/5, so plus 6/5 B, and minus a fifth A. So now 3/5 A, take away the 1/5 A at the end, simplifies to 2/5 A. And then the minus 3/5 B plus 6/5 B is plus 3/5 B. So X to F as our final vector, well, that's going to be equal to 2/5 A plus 3/5 B. Oh, really? Is it really? I mean, really? Okay. So what that's telling us is exactly the same vector as the first vector that we worked out, right? So we worked out the first vector, dx. So dx was equal to 2/5 A plus 3/5 B. And we've worked out that xf is also equal to 2/5 A plus 3/5 B. Well, they're the same vector, so therefore they're parallel. Yeah. Dx and xf are parallel, and they share x in common. So they have x as a common point. So therefore, dxf is a straight line. Okay. Yeah. We'll move on to the next question.